Hi, welcome back to the breadboard. Today is day 3 of IoT week with Texas Instruments, Tuesday the 31st of May. So we're getting well into our project now. We've already selected our board with the Texas Instruments Launchpad CC3200, and we've got our temperature sensor, which is a TMP275, up and running with the Launchpad, and we're currently just setting the data out on a serial port. So today we're going to look at putting a display onto the Launchpad so we can actually see the readings locally using a Sharp 96 LCD display. This is a special display. It's very, very low power. It has a resolution of 96 pixels by 96 pixels. I have some other displays that I want to show you. We're not going to actually go and try coding them and get them up and running in this particular video because I've already decided which one I want to do, and I only have one which will actually plug onto the Launchpad anyway. But I want to show you the other ones because they are options if you're designing your own system that you could use for display outputs, and they vary from everything from a 16 line by 2 row up to a full 10-inch high resolution intelligent display. So there's everything from completely being driven from the Launchpad to being just sent basic information. This is effectively regarded as an HMI, a human-machine interface. Anyway, that's a bit overkill for creating an IoT node. It would be great for a central control system, but not for the node. So we're going to be using the Sharp. But let's have a quick look through these different displays just so I can show you what they look like. Okay, so what I have here, let's start with the probably the simplest and easiest ones to describe. These small modules. You can get these from all sorts of places, and what they are is 16 characters by 2 row displays. What I like to do with them, they actually have a parallel interface on the back here, but I like to add these little boards that allow me to talk to it with either SPI or I2C, and it takes just a 2-wire or 3-wire interface depending on what you're using, and it'll convert it into the parallel interface. This one is just happened to be in a 3D printed case with an I2C interface in this case coming out on a little header. So it's a 2-wire interface with power, and that works very, very well. And we will look at using these kind of things with the Launchpads and stuff in other videos. This bigger display here is 20 characters by 4 rows, so you can get a lot more information on here, but you basically drive it the same way. This is a fairly industry standard interface here, and then just with a serial port or serial adapter. This one happens to be an I2C interface on here. Now this one is a small about a 3.5-inch LCD display. This one happens to be on an adapter for an Arduino, but you can also get them for the Launchpads from the TI Launchpad website as a Boosterpack. Not this specific LCD, but ones that are very, very much like it. It'll be very much the same on how you drive them. What they have in some cases is a parallel port, maybe 16 bits or something, that you write to and then you strobe the data in, and then other ones have a SPI interface. I'm going to save the Sharp one until the end. The next row of displays I have are these 3 here. We've got everything from a little 2.4-inch display, a 3.5-inch display, and then I have also this 7-inch display. Now the way these work, they're all basically the same, is that you've got a TTL serial interface. So, you know, the Launchpads, Arduinos, Raspberry Pis, etc., they all have a serial port on them. Often it's used to talk through the USB to the PC, but you can actually tie into these. The idea is you use a design tool to lay out your screen and designate active areas and buttons and things. There's a touch panel on all of these as well. And then all your application has to do is know how to send a command and say, hey, put my temperature value into this particular text area, and everything else, the graphics, all that kind of stuff is done for you. So it makes it very easy to put a high quality display onto a small microcontroller or something. You don't have to load up these huge libraries in order to get a good display for a human machine interface. Now the last one we're going to look at, which is the one that we're actually going to be using in this case, is in the form of a Boosterpack, which is the 430 Boost Sharp 96. These displays are really cool in that they are 96 pixels by 96 pixels. They're effectively just a memory map, so you just stream out the memory to them. You can't read from them. and they're actually using a SPI interface. And if you look at the back, there's a few things on here, resistors and stuff, to do with interfacing the touch sliders on the side of these this booster pack, and also for an option of different power supply for the LCD display. But at the end of the day, this display takes microamps, if that, and once you write to it, it's very much like e-paper or something like that, only it's a very, very highly reflective silver and white display. When we get it going, you'll see exactly what I mean. And it takes so little power that if it was running and I actually pulled it out of the launch pad, the display would be on there for a little while, even several minutes before it slowly fades away. Now, the one peculiar thing about these display is because of the nature of the display, it does have an issue where it can get polarized. So you have to, in the background, have a clock that's alternating the polarization layer of this display, and we'll look at that in the code if it's there. And what it does is it maintains the high contrast ratio and stops it getting charged more one way or the other. It won't damage it if you don't do it, but the display will kind of go funny and you'll take a little bit of work just to get it back to normal. In our case, we're going to use a library that's already been set up for this, but we can have a quick look in the library and if we can see that routine that would be doing that for us. Anyway, without further ado, let's get to setting this up. Now, I'm going to have to rearrange the CC3200. Right now, with the CC3200, I've got my temperature sensor on the front of it. So I'm going to move these wires onto the back because the sharp display here, it is not a stacking display. It's going to be the very last one on the stack. And because it's a display, of course, it's only natural that it would be. So once I've got this on here, I won't be able to plug anything else into these top pins. So I'll plug my temperature sensor into the bottom. So let me just rearrange that and I'll show you what it looks like when we're done. And then we'll get to the PC and start looking at code. Okay, so here it is now plugged in. As you can see, it just stacks on the top of the Launchpad extensions, and I've connected my temperature sensor now to the bottom of the connector instead of the top. We will have to move it one more time when we get to putting a battery pack on here, because that will also go on the bottom, but that will be the only time we have to move it. Ideally, if you're going to make this into something more permanent, you could put a simple strip board on the very bottom with some headers that it would all stack onto, and that would make it much, much easier, and then you could actually mount it onto something if you wanted to. And maybe after this project is over, I'll actually build up a little strip board so we can do that. And the nice thing about the launch pads, by the way, which I like over and above the Arduinos, is that these pin strips are actually all 0.1 inch space. There's no funny offset with one of the pins that precludes you from using a straightforward strip board like you have with the Arduino. These launch pads, you can just put 2 rows on and put it straight onto a strip board or a pad board to build up your prototypes quite easily. Anyway, let's get this plugged into the PC and we'll now look at some code and get it up and running. Okay, so we're here at the PC and we're looking at the user guide for the Sharp 96 booster pack, the 430 boost Sharp 96, and this is the pinout of it. When it plugs into the launch pad, it's got 2 rows of 10 pins. The launch pad we're using has 2 rows of 20 pins, but we're only using the outer ones for this particular booster pack. So it shows you which pins it's actually using, and a lot of these we can actually ignore. So we definitely need the 3.3 volts. We need the LCD power control and the LCD enable, and we need the external COM inversion. This is the one I was talking about that does the polarization thing. And we need the ground pin. We do need the SPI lines here as well, but these 3 down this left side, which is the slider and the right side slider, we don't need those. We can ignore them. Now, I'm not going to bother putting a wiring diagram up for this because literally you plug the LCD display straight into the launch pad. Now, some of the things I just want to point out, this is the Sharp display, and it's actually based on the LS013B4 DNO4. It's a 1.35 inch PNLC memory LCD. So that's what I was saying before, is that when you write the memory, the actual memory location is literally the pixel of the LCD. A lot of the other LCD color displays and things, the memory is actually separate to the LCD, and then there's a controller on board that maps the memory onto the LCD and effectively refreshes it. In this case, it's literally a static display where you write the memory locations, and then you just have this little inversion pulse that makes sure that the display doesn't get polarized one way or the other. An important thing to look here is that it only consumes 10 microwatts of power. That's insanely low powered display. So yeah, it's a pretty impressive display. Should you choose to get these displays and put them onto your own board, they're actually use a 10-pin connector. It's a very small connector on the board, but you can see here you've got the clock, you've got the serial in, you've got the chip select for the SPI bus. It actually doesn't have a data coming out, so there is no SO. COM inversion, and then you've got the display on off signal, power supplies for analog and digital, a control pin for external or internal inversion mode, so you can either send it data or you can use a pin to do the inversion, and then the ground, two ground signals, one for analog and one for digital. There are full sets of libraries for CoComposer Studio, IAR, and or Energia, and we're going to be using the Energia libraries because that's what this whole project is about. The CoComposer Studio is far more complicated IDE to use, and I don't want to get into that for this particular project. Anyway, let's get to the code. So what we have here, this is the code that we had finished up with yesterday, which was reading the TMP275 temperature sensor and sending it out the serial port, and it just does that every second. And you can see on the right hand side here, connected to COM21, that's exactly what it's doing. I plugged it in about well, a little while ago. That's why it's up to 1,600 seconds, and it's about 22 and a little bit degrees centigrade in here. And as you can see, this bottom bit is a real-time image of the Launchpad with the LCD plugged in and the temperature sensor. Now, fortunately with Energia, there is a sketch already provided and a library that comes with Energia now for the Sharp 96 display. So if you go into examples and scroll down to the LCD Sharp Boosterpack SPI and load this up, all right, so we just loaded that up now. What this does is gives us a bit of an example of how to use this display. I've actually written drivers myself in the past for it, but now that these libraries are available, we're just going to stick with these. So you can see here what we need to do. You need to include the SPI library, a timer library, and a Sharp Boosterpack library. Initializing the class, setting up a couple of statements. Now my count is actually not used in my application. This is part of the demo that you're going to see. I'll run it in a moment. You can see what it does. So this is the one that's provided, and it provides us enough information about setting the position for printing, how to send out the data to the LCD screen, etc., that we can derive our own application from it. So if I just load this one just to show you what this demo does, and if you have a Sharp 96 display, you'll be able to do this too. It will work on a number of different launch pads. So let me just run this in right now. It should go in. It's uploading at the moment. We should see it come up on this screen any moment once it's done uploading. Okay, it's done. There we go. So it's now running through its demo on the screen. So you can see there, that's basically what it does. So you can see you can set the rotation. It's this My Orientation, and it's setting the 90 degrees, 180 degrees, 270 degrees, or 0 degrees. So you can actually rotate the display around to suit your needs. And you can see it's quite flexible in how quickly you can update data to this display. But remember, it is just a 96 by 96. And there are two fonts available, font 0 and font 1, and we're going to be using both of them in our example. So let's get rid of this particular one and let's load up. I've already added the code in derived from this and added it to the temperature software that we were using yesterday. So let's just bring that up and have a look. Okay, day 3. So here we have it. So I've included the Sharp 96 LCD display includes, which is the SPI bus, the 1 millisecond timer library, and the actual library for the Boosterpack. What I've also brought in for the Sharp display is the orientation and then a screen delay. So how often am I going to update the screen, and a timer for that screen. Now, if you remember yesterday, we went through this, so I'm not going to describe how that particular piece of functionality works. If you don't know and you didn't see yesterday's video, go back and have a look, and I do explain it. In the setup, I've added one more function, which is calling the initialize Sharp. That's all it does. And in the loop, I've added one more function, which is called update screen. So I'm not going to go through all of the other functions that we did yesterday. I'm only going to look at those two. So here is the init Sharp 96. So we start the Sharp library with the Sharp 96.begin. You can call this whatever you like, by the way, the 96. That's part of the class initialization here, right here. So LCD Sharp Boosterpack _ spy space Sharp 96. So you can change that name and any reference to it to whatever you like. We tell it to clear the buffer, which is the local memory buffer, not the actual display itself at this point. We set a font. Now I told you there's two fonts, 0 and 1. We then write at some text to the display at 1010, which is 10 pixels down, 10 pixels across. And we write TI IoT weak out to the display, and then this little loop here just writes a pixel. So you can see here it's doing something different. It's just setting XY. We're telling it the X and the Y coordinate, and then to set a 1 to set it to on. So here we've got the update screen routine, where what we do is if the screen time is elapsed, so this is that routine that we went through yesterday, then we're going to do an update to the screen. If it hasn't, we're just going to exit. So we're not wasting time continuously updating the screen. So we set the font to font 1, which is a bigger font. We set the position to 40 characters down and 40 pixels down and 10 pixels in. We then simply use a Sharp 96.print. Now the print pretty much functions the same way as the serial.print does. And we give it the temperature, and then we give it the C symbol. So we're going to put like 25.36 C for the temperature. We then change the font to a small font, which is font 0, and we set the position to almost the bottom of the screen. So this is 9 pixels up from the bottom of the screen, and we're going to write the elapsed milliseconds since we powered this up. So it's going to say the time, space, and then whatever the milliseconds is divided by 1,000. So how many seconds since we started. Now all of these prints that we've currently done, nothing has actually appeared on the display yet. And it's this Sharp 96.flush that will actually update the display. And then the last thing we do is reset our screen update timer, and then we exit and everything goes away again for another second or whatever we set this to be. Anyway, that's all of the code that's actually required to make this Sharp display work. I do want to have a quick look in the LCD Sharp Boosterpack spy.h so that we can actually see a little bit of these libraries just for a backgrounder. So let's just go do that. So I've loaded this up into Visual Studio just for ease. So if we scroll down here, you can see there's a whole bunch of includes for the Energia, for a Terminal 16 and a Terminal 12 font. So these are two different fonts. They're basically just character arrays, and you pull in the relevant set of pixels for the character that you're wanting to display. It re-imports the SPY header and then this 1 millisecond timer. So we have an enum here that has a couple of functions for when you're writing text and things to the screen. You can have no wrap, so it will go to the end of the screen and basically run off the side and you won't see it. You can have a wrap where it goes back to the beginning of the same line, or you can have a wrap where it goes to the beginning of the next line. We've got two types of fonts, so 0 and 1. We've got the print, which basically is a constructor overwrapping on the existing print functionality. We have the begin function, who am I, a clear buffer, a set orientation, which allows you to do that screen rotation. You have a set reverse, which allows you to do the reverse pixel. So instead of a white on black, you can do a black on white. We have a function for setting the font, setting the line spacing, set XY with a value, printing text with a string, and then specifying the wrap type, and specifying text where you're just specifying a character. We then have the flush routine. We have a set coordinates which we use for the print function. Like we can set the coordinate first and then just use a regular print. And we actually have a function where we can draw an image as well. Now if you look in the C++, I'm trying to just go through this quickly. If we go down here, what I'm looking for is something that sets up an interrupt handler for the inversion bit. So the begin routine is setting up the display as well. Chip selects. If it's auto VCOM, it's calling a routine to enable the VCOM toggle. So we should go and have, that's probably the one that's setting up the interrupt driven one. But what you will find here is when we actually get to the routines that actually write to the display, they will have something consistent about them. So flush, for instance, you see this VCOM command here. That's going to output a VCOM toggle inversion. So here it's calling the set toggle VCOM command. And what this is doing is actually telling a function to, it's the function it's calling, this send toggle VCOM command, is actually sending this inversion bit in software through the SPI bus to tell it to toggle this internal value that keeps the screen from biasing itself one way or the other. But what is important here is this bit down here. This is just getting set up. It's a structure for the 1 millisecond task timer. So at the very beginning it said if VCOM auto. Okay, now and what that does is actually does this TAO enable VCOM toggle. And what's happening here is it's calling the 1 millisecond timer and it's giving it the structure, which is this one here. So it's telling it that every 1,000, I think probably microseconds or probably milliseconds, once a second, it's going to invoke this function with these two parameters. So the send toggle VCOM is, as I said, is what's being called by all the other functions that write to the display. But just in case it's not being done frequently enough, you can have this auto timer continuously doing it once a second, just sending out the toggle, and so you don't have to remember to do it as a coder on your screen. So here it is here. If auto VCOM, tau enable VCOM toggle. And that's what we were talking about. So if the auto VCOM is enabled, it will set it up, and then every second it's going to do it for you. So back to our code. I've already run you through this, so the only thing left to do now is to actually upload it to the display. You can see here it's still running the demo that was part of the libraries. So let's just upload this up to the CC3200 and see what happens. I haven't removed the serial port timer yet either, so that should also still be there and running quite happily. So it's downloading now. It's done. Sorry, it's there. It's working. What am I saying? So you can see here now that the display, let me just make that a little bigger, is now TI IoT week with a horizontal line underneath it. Here's the word temperature, and it's updating the temperature here, and there's the seconds elapsed that's ticking away in the bottom. And just to show you, I'm just going to stick my finger on the sensor now. So there's it creeping up because I've got my finger on it. Now if I just let go, it should settle down and start coming back down again. Okay, so that's it working. Nice, simple, and easy to do. And we now have our display. And if I bring up the serial port, we also have the serial port running quite happily. And just to show you that timer function, just to close off here before I go, I will change the serial port time here, the serial delay. I'll make that every 10 seconds. Let's just upload that again. So you're going to get 10 updates on the LCD screen and then 1 update on the serial port. So you minimize your debug traffic effectively. So that's 2, 3, 4. When that bottom one counts to 10 here, it should then send a signal out and we should see something come up in here. There. All right. So 23.44, which obviously this is slowly coming down again. And then when it gets to 20, 16, 17, 18, 19, there we go. That pretty much concludes day 3 of this. We've got the LCD display working. We've got temperature readings happening. Tomorrow we're going to look at using this reading and see if we can output a control to turn a fan on and off. In response to maybe going over 25 degrees C, it'll turn a fan on, and when it gets below a certain threshold, maybe 22 or something, it'll turn the fan back off again or something. That's for tomorrow, and I hope to see you then. In the meantime, have fun.